Okay. Now it's time to get back to work. Let's hope the questions today aren't too difficult. Hopefully just a bit of a warm-up. Still waiting on Google. Have not heard anything back. I think I'm probably gonna send them another email after this stream. Hoping to get team matched if I end up actually getting team matched and getting the offer, hopefully by the end of next week. That'd be nice, because I mean it's been almost a month now since my final. That sounds like that sounds like hopeful dreams more than anything. All right, I think this is gonna be everyone we're seeing. So let's go ahead and ready up, see what we got. Repeated addition. Given a positive integer n, sum all of its digits to get a new number. Repeat this operation until the number is less than 10 and return it. Cool. So, the obvious sort of way to do it, there's two ways I think that you could tackle this. You could do it by, one, converting it to a string, and then you sum from 0 until length minus 2. Because the last character, if we've removed everything else and we just have the last character, it'll always be less than 10, so we don't have to sum it. However, this is slow because we are working with strings, we're converting it to a string, and then we're doing like string accesses. Though time-wise, it might be, I think maybe the same as the other way of doing it, but I think the better way to do it is to use a property of integer division where if you take a number and you mod it by 10, this will always remainder of last number. So this right here is I think what we need to do. We need to utilize this property to do the addition. I am going to adjust my incredible lighting setup here a little bit. There we go. Make it a bit more consistent. So I think, because looking at what they're doing here, huh? 2 plus 4 is... Oh, I misunderstood the question. So, we're going to do... So yeah, this property is still something that we're going to use. However, we're going to do a nested, I think nested while loop. I think so. I can't really describe this in words. It's kind of confusing. So let's go ahead and do while n is greater than 10. We're going to do int temp equals n. What we're going to do then is to say temp equals n, while temp itself, we sum. So let's keep track of the sum number as well. So, hey Snailman, good to see you, welcome. So, we need to do this for every number in this. So, while temp is greater than 10, cur sum plus equals, we're going to add in temp mod 10 to grab the last digit. And then we're going to do temp equals temp over 10. And the only thing I don't exactly remember is if dividing like 5 by 10 gives you 0. Let's just try 0 here. And then we need to say n equals temp. And here we're going to return n. So we're going to assign bravo. Okay, and we're going to return n, and this I believe, so return the sum after it is less than 10. Greater than, not equal to, but greater than 0. Really? I guess greater than 10. Try that. Okay, we got 8. That's okay. Let's do this, right? Println, we're going to print out per sum. Just to see what this current sum value is. So it's 16, 8 times 2 is 16. We should have, oh, it's, huh? Okay, now I'm a little bit confused. So we're gonna do, ooh, that's gross. Yeah, it's a, what am I even, okay, let's make sure I'm actually, what I think is happening is happening. I mean, yeah, that's exactly what I think is supposed to be happening. And let's make sure this is doing what I think it's doing. So it takes a 5, adds a 3, adds the 8. Okay, then what I missed here was to say here's sum plus equals temp, because now it is less than 10, so we need to add it to the sum. That should do it. Still no. Then we also need to actually, assign this to the right value. There we go. Let's get rid of this. Let's get rid of this println. And let's get rid of this println. Cool. Has to be less than 10. All right, let's see what this next question here is. BINARYSEARCH, given a list of integers, there's mathway. Really? Yeah, pure math questions are my weakness. Okay. More pattern-based, really? Let's see what else we got. So, this second question. the fact that this can be done in a one-liner is kind of funny. I guess it's like the third option. Hey man, good to see you. Hop on in. Hop on in. I haven't even looked at the other two questions yet. So given a list of prices representing prices for cars and a budget K, return the maximum number of cars you can buy. This session's over. Oh goodness, that. Okay, this one, we want the maximum number of cars with budget K. What I think we need to do... Okay, what we need to do is, because we're looking to buy the most amount of cars, we don't care about the quality of the cars, we don't care about anything. So to get most for our money, we always want to buy cheapest. So, because we want cheapest, this automatically makes me think of a greedy algorithm. And to utilize greedy algorithms, we always want to sort. So we want to sort it, and then keep buying cheapest until we run out of money. And I think that really should be it. That's not a particularly difficult question. So let's go ahead and do that. We're going to do arrays.sort prices, and then we're going to do while k, actually, let's do let's do a for loop. I just want the index. I is less than prices.length minus 1. I plus plus. Cool. So we're going to say if k is greater than or equal to prices at I. I don't actually think we need to keep track of a counter, but I'll do it anyway for readability purposes. Because the counter is always going to just be equal to I. So let's make a variable up here called int purchase equals 0. We're going to, if we can buy the car, we're going to do purchased plus plus k minus equals prices at I. So we're going to buy the car, and we're also going to take away the money. And the instant that we can't actually purchase anymore, there's no point in iterating through the rest of the array because that's just wasting time. We're going to break out of here. And down here we're going to return purchased. These two easy questions have been quite nice. Ooh, that's the wrong answer. Okay. See, because it works here. My result was 2. Interesting. So, let me pull up a calculator real quick. 155 plus 64 plus 42 is 261. So it's exactly the amount that we need, right? There we go. Easy. Ooh, that's slow. Why? Curious as to why that is as slow as it is. Okay, let's see. How can we... What's the actual topic here? Yeah, greedy and array. Not really sure how we can speed that up, to be completely honest. Like, this seems like the... Ooh, maybe it is just binary search servers freaking out today. Not even sure if there's a better way that I can, at least not a way that I can think of off the top of my head to do this. Is it just going to be sort? The cheapest cars always get the most cars. Maybe sort them by price? Yep, easy solution to this. Okay. Alright, let's see what this third question is. I saw palindromic tree show up in the chat. Okay, bonus, solve an O of H where H is the height of the tree. Given a binary tree root where each node contains a digit from 0 to 9, return whether its in-order traversal is a palindrome. So in order is the sort of the trivial way to do this, right? So trivial way is to do an actual traversal, and in order traversals, as we know, are left, then center, then the right node. So the in order for this one is 1, 5, we go here, we take 9, and then we go to 5, and then we go to 1. Man, I remember in my data structures course, these traversals would they would hurt your brain, because I mean, once you sort of nail them down, or once you understand them, they make sense. But figuring out how you go from 1 to 5, then hop down to 9, back up to 5 and 1, it was not a fun time trying to memorize these. Especially when, you know, one of the quizzes that had a major chunk of your grade on the line depended entirely on these. Still think by far the worst thing that we had to do, in difficulty-wise, was the quiz on, I think it was red-black trees and AVL trees. Because it wasn't even like, you know, what is the rule that a red-black tree follows or this? It was like, hey, given this starting tree, and that it's an AVL tree, and like these 10 operations, perform them on the tree by hand, like performing the necessary rotations or like color swaps for the red-black tree and whatnot. But it's like, I understand that red-black trees are important, that I think there's a couple data structures at least implemented in Java using red-black trees. However, doing the rotations and like color swaps on paper was not fun. Granted, I could just kind of do red-black trees in my sleep by the end of it, so maybe it was a purpose. So let's actually go ahead and do a... Okay, I think the way to do this, right? It's a bit of a dumb way, but you could use a double-ended queue, add everything in, and let's do it the trivial way first, right? We're gonna do the trivial way. Could add it maybe into like a double-ended queue and then go from the front and from the back and then compare the two, remove from front and back, and then that'll allow you to do it. However, that's very space intensive and I don't really want to do that. So has to be just like a recursive thing we can do here, right? Like, I guess I can try just solving it recursively. So let's think about if we are to do a. So first thing we're gonna need, right? We're gonna need a result from the left subtree and a result from the right subtree. Recursion Go Bert, welcome. So that's got a very, very familiar name, but I think it's been a bit. So Boolean left equals, obviously, we're gonna traverse root.left. Slow today. Okay. So root.left, and we're gonna see the solution from the right. I'm trying to avoid doing this. I really don't like how if you control backspace, it like removes the space before the previous word. Just string and then... Okay, so we need to traverse left, take this one, because we need to do left, center, right. Do some stuff with this node, and then do the right node. But how? So we traverse left. I think the best you can do. maybe has to be a way, right? Let's have like a stack. The left side, and then pop whenever you. Okay, let's solve this trivially, and then we're gonna go the other way. Yeah, I'm gonna do it that way. Okay, let's try the newbie solution, right? Let's make a string builder. And let's do that level order traversal. So let's do public, not public, let's do traverse root. And return the s dot is palindrome the s dot toString. We're gonna have to write both these methods. So the first one, so public void traverse we're going to do tree root. Cool. So we're going to do traverse root dot left, traverse root dot right. First things first, if the root node is null, we're going to just return out of here. And we're going to then add ds.add. I think it's append actually. We're going to append root.val to it. Easy. Then let's go ahead and solve this palindrome. So public boolean is palindrome string. Great, so this one should be fairly simple to do. I mean, so we're gonna just do a for int I equals 0. We're gonna traverse halfway through. If s.char at I does not equal s.char at s.length minus 1 minus I. I'm going to return false. Otherwise, if we've made it through the entire thing and it hasn't failed, we're going to return true. That should just... I'm waiting for the compilation errors. There's no way, I was going to say, there's no way I did this right the first time. Perfect. And if that was the only one, really, yeah, it's going to be a super slow solution, but it's a solution. It's kind of breaking it up into two separate chunks and solving them that way. Not ideal in the slightest. There has to be, because you can solve it at O of H space. I think O of H space does imply sort of like space kind of makes me think of a stack. Because it'll only ever be H deep. Oh boy, binary matrix leftmost one. You are given a two-dimensional list of integer matrices. Okay, which contain ones and zeros. Given each row is sorted in ascending order, with zeros coming before ones, return the leftmost column index with the value 1. If there is no row with a 1, return -1. Interesting. I mean, you could technically... maybe keep a stack for the left and right. And when one empties, you just look for, or wait, maybe, what about a double-ended queue? You might be able to use a double-ended queue. No, but that's not O of H. This is kind of a problem that's interesting because it's something similar to what I had to solve for our game. When I was building the level parser, our ground, you draw in a bunch of ground tiles and you need the parser itself to break that ground up into sort of rectangles that you can use. So what I did was something similar to this algorithm where pretty much if I find the top of a block, I'll go as far as I can this way and find the minimum depth pretty much. So the ground could extend like this, like that, like that, extend down here. But I only want this rectangle, so I'd find the minimum depth of this rectangle, and then I'd draw that in, remove it, and then continue searching, and that allowed me to do it pretty fast. Choose to count left nodes and right nodes. Man. Then add to stack up at midpoint. This problem is very has a lot of depth to it that you can just kind of avoid if you don't think too deep into it. Okay, let's see. Let's just solve this one, right? So, Boolean found 1 equals false. Int 1 call equals 0. So return the leftmost column index. So this would be 1. Yeah. So let's do that nested traversal. J less than matrix at I. Dot length, I think it's going to be a square matrix, so that doesn't really matter, but just in case. Okay, so if, I think what I need to do here also is set this to matrix at 0 dot length. So first of all, right, if j is greater than 1 call, we break from this loop. I think this one is going to be all about efficiency. So if we know that we are higher than our leftmost column, we can't find 0 at smaller, we can't find 1. Okay, cool. Then, if matrix at I, j is equal to 1, and j less than 1 call, pretty much if we find 1 more to the left, if not found 1 equals true, to make sure that we know that we have actually found a 1. And then we're going to say 1 call equals j. We can also break out because we know anything further will be more. More breakout. All right, down here we can say pretty much return. Oh, let me see if we can know how to use these. Found 1. Let's capitalize this because it's less of a change. Okay, found 1. We're going to return. I think it's a question mark first. Return 1 call else return -1. Is that how you use ternary expressions? Maybe it isn't. Maybe it is a column and then a question mark. I've always wanted to learn how to use these, but I've never gotten the chance to. Okay, let's look up Java ternary. Let's see how they work, right? Okay. Boolean expression, question mark, this, colon, that. So I was right the first time. Question mark, this, colon, that. This isn't even a. There you go. I think that should be it. And this should be a -1 rather than a +1. Runtime error, index, line 8. I always, out of habit, make that an I. Okay, yeah. We're gonna return a -1. It's always these edge cases. This is why I never participated in something like ICPC, like the programming competition, because I cannot be asked to chase down edge cases without having anything to look for. Turn that -1. Easy. Cool. All right, now that we're done with this, let's go ahead and try and come up with a more clever solution to this one. So what can we apply, right? We know, just purely based off of that bonus hint, that an O of H solution is possible, where O of H is the height of the tree. What we want to know is, because we would, to check if something is a palindrome, we would need to know we need the rightmost node, right? So how exactly in O of H space, where H is the height of the tree, I guess what we can maybe do is, that wouldn't be O of H. I was gonna say what we can maybe do, starting from the root node, we can do a traversal of the left, keep that in a stack, and do a traversal of the right and keep that in a stack. But the issue then occurs that we just have 2 stacks of O of H, which is just O of N. Could potentially, right? We could potentially do a traversal to count the amount of total nodes in the tree. So this right here is a working solution, but we don't want that solution, right? So let's copy the solution down here. That. So what we can do potentially here, let's get rid of this, okay, is to do a traversal. We want to count the number of total nodes in the tree. Then make a stack to store, that's not O of H. That's O of N over 2, which is still N. I don't get it. I don't understand how you can bring that down to O of H. What H are you storing here, right? I guess maybe Well, no, because... No, that doesn't work either. I was gonna say, maybe you could, like, traverse all the way left, but then you also need to know the rightmost node. The issue that we're having is that at any given point, we need both the leftmost and rightmost node that are available, because those two are the ones that we need to compare. Unless we can maybe like traverse halfway down the tree and then from there traverse one down and pop one off the stack. I just wanna take a stack DFS recursion. I mean, I'm seeing stack. Because legit, my best guess is it's not O of H, but my best guess is to store, make stack to store 0 up to n over 2 in stack. And then, afterwards, after we store n over 2 in stack, we can just continue traversing. Every new node we see, we pop from stack and compare. That is a way to do it. I don't know if that's going to be the best way to do it, but it's a way to do it. Once again, though, I don't even know if that's going to be faster than my initial solution, because depending on how much space, I mean, it does take up half as much space, but you are using twice as much computing power as my first. So, I mean, technically it uses the same amount because we need to traverse through the tree once. Still not O of H though. Hot potato? That is a hot. Okay, hold on. Hot potato algorithm. Sorry, what? There's so many of these cool algorithms. Okay. Ooh, first things first, I'm going to re-enable my dark mode because I'm not reading white mode Wikipedia. To autonomous when interconnected in multiple locations. Hot potato rack. Okay, that's in fact not what I wanted. Dang it. Okay, yeah, hot potato. Just, you know, the concept where you toss like the children's game. I might be missing something entirely. I probably am missing something entirely. Okay. I don't know where to go from here, man. I'm gonna look at a solution. I need to give me a nice Java stack one. Okay. Yep, means to go left node, right child. To yield the reverse, in order we go right and right node left. We simultaneously perform in order and reverse order and check equality of values. We cannot go for simple recursive implementation as we need to perform two traverses at once. We use two stacks for iterating. Wait, what? So double-ended queue, okay. Push all left, push all right. So while they're not empty, we pop we pop from the stack, we compare. Um, I mean, okay, this makes more sense now. That's very, very clever. Okay, here's what I'm gonna do. Let me grab this one and paste it in, and we can kind of dissect the solution. Okay, I'm gonna need. I think I copied pretty much everything. Cool, accepted. It's still not very fast. Now that I think about it, mine might have been faster. Okay. So, what we're doing is we're making this queue, making the stack. Keep track of our nodes. Then, add cur to stack for both. Have n log m for binary matrix leftmost one. Okay, and then we pretty much so we now we perform in order and reverse in order. So yeah, we grab the node from the top, we check it, and we push the, what's push all left and push all right doing? You push node, so you push as far left and as far right as you can go. Very interesting solution. This is not something I would have come up with. I did have a similar sort of idea, except mine didn't exactly meet the O of H space criteria because it would store n over 2, which would n over 2 items, which would still be O of n, or in worst case. Okay, so let's go ahead and go over the time and space complexity of our solutions to these questions. So repeated addition. I was told that there is a O of kind of 1 mathematical way to do this, which very cool, very interesting. Who had the O of 1? Who had the math one-liner for number 1? Cool. So my solution runs in, oh goodness, I assume this is O of n time. It's very difficult to pinpoint time complexity for things like this because we're not really like increasing the input, we're increasing what the value of the input is, and like the input could be the same number of digits, but it could be, you know, like 1111, for example here, and this would run in one iteration. So I'm going to assume it runs in O of n time, and the space complexity is just constant because we are just using these couple of variables. Then, we're going to go into buying cars. Buying cars is instantly made me think of a greedy solution just because it's asking for the maximum number of cars that we can buy, and we're just given the prices and the amount of money. And logically, if you're trying to get the most for your money without caring about anything else, your best case is going to be always looking for what the cheapest thing is to buy. So what we do is we sort the cars, which automatically puts us up to n log n time complexity for whatever sorting algorithm it has implemented. And then We iterate through and just continue to buy cars until we can no longer buy cars. Otherwise, once we reach the point where the next car is too expensive for us, we just break. And that's going to be it. And we return purchased. So this is going to run in O of n log n for time, and O of 1 for space. O of 3k, thanks for the follow, man. I really appreciate it. And it's going to run in O of 1 space, because all we're doing is keeping track of these variables, never really making any sort of larger data structures. Cool. Let's go ahead and move on to the next one. Palindromic tree is a very interesting question. We can go back to my first solution because I feel a bit more proud of this one since I kind of came up with it and didn't just take it from a solution. So let's go ahead and copy this solution in. There you go. So the insight behind this, right, is obviously if the bonus is asking us to solve it with a O of H time complexity, I knew automatically that there had to be a better way to do it than this, but after a bit of thought, I couldn't kind of come up with it. So I decided to go for the trivial solution first. All it's asking is if the in-order traversal is a palindrome. So my mind sort of split that up into two separate problems. Its in-order traversal is one thing, so we can just take an in-order traversal of the tree, and then check, is a palindrome. I even wrote out the solution to the easy is palindrome question in here just to do that check. So what I'm doing is I have one function called traverse, which does an in-order traversal of that binary tree, which is in order is left, center, and right. I've also heard it seen it written as left, node, and then right, or LNR. So I did that traversal, and I appended to the S, which is just a string builder to avoid having to do a string concatenation and making a new string object every single time. So once I did that, once I traversed, is it possible to do constant space? Honestly, I don't think it is. I don't think it's possible to do constant space for this one. That seems a bit like if we struggled to bring it down to O of H with the stack, I doubt that we can do it in constant space. Quick select. Oh man, quick sort sounds familiar, but quick select not so much. I'll have to look into that. But yeah, and then we just, once we get the string, we literally just check if it's a palindrome. Easy. I think space complexity would be O of n, since for every node we are adding more to this string. Time complexity I think would also still be O of n because we traverse the entire tree here as well as in the palindrome. Binary matrix leftmost 1. This question was kind of easy if you have a forward and backward iterator. I mean, you'd have to like, I guess the whole iterator thing, if you could do it where you somehow were able to like, I don't know, find the leftmost in the traversal, find the rightmost, and then you would somehow have to like iterate backwards from them without ever storing anything. Which, I mean, because it's just, oh, this seems like a recursive. The math one-liner was the first problem. Let's see. Hold on. I want to see that math one-liner. Where was it? Return 9 if 9 mod 9 equals 2. Return not. Wait, really? Is that just it? Okay. So, that's I guess that. So I guess here. I don't understand how that works. I have no clue what that is. I have no idea how that works. It kind of scares me a little bit. So, I guess this just seems like a recursive nightmare to me, honestly. You'd have to, like, maybe just do like maybe if you do a in order, reverse order, I think that makes sense. I have a write-up in solutions. Yeah, I'll definitely take a look at it once I finish this couple. The thing that throws me off here is that we need to keep track of two separate recursive stacks, and I cannot think of a way off the top of my head to do that, but like keeping them at the same time, because you'd have to like compare, then go up a level, compare, go up a level, compare, and eventually you'd end up like overlapping, and then they would just keep comparing that way, and if each one of those returns true, then you should be fine. So I guess in theory you could do it in O of 1 space, but that O of 1 space is so far beyond me. This one I initially thought might be a bit more challenging. Yeah, it's log n. Very interesting solution. It's definitely not one that I think I could implement. So yeah, for this one, I pretty much I kept track of where the leftmost one that we found was, and then I kept track of if we'd ever found a 1, just so we could use that down here. Pretty much I iterate through it as you would any 2D array. And once I figure out that we're either past the point of our previous one, meaning everything else would be a worse solution, I just break, because we can continue going on to the next row since we know everything in this row will be a worse solution after that. Then I check if we're still good after this. I check if it's a 1, and if this 1, this check here is redundant, because if we made it this far, implementing binary search is a bit better for this one. It might be, because I mean, man, it's never been like a comfortable sort of topic for me to just, not topic, but like a comfortable skill to just like implement binary search into problems to find ones. Although I do see what you mean, it would reduce the search from n per row to log n, and I do see now how you could bring this down to n log n. Let's see. The n log n. Binary sort is hard. It's not in and of itself, the idea of it isn't hard, but implementing it correctly so you're not missing anything is the hard part. Yep, so it is binary search array. Perfect. So yeah, we're just, for each row, the leftmost is the minimum of, leftmost is going to be the minimum of the first one found through binary search, and leftmost column index. A lot of pitfalls. I remember, I think I had to, it was for one of my harder OAs, I had to like implement binary search in a question, and I think I spent most of my time just trying to implement the stupid binary search. Though, don't get me wrong, anytime you need to find something, being able to bring your search down from n to log n drastically speeds things up, and I feel like in an interview setting, if you can do it confidently, I feel like, go for it, do it. But if you can't do it confidently and you're going to spend more time implementing this binary search than you are in anything else, I don't even know if like it's worth it. I feel like you could bring up at that point saying, hey, to do this we could use a binary search, though, it's like hey, I'm not entirely like confident implementing it, but this is, if I had more time and more resources, I feel like you could just say, like if I had more time and resources and access to make sure that I could implement it correctly, I would swap out this linear search for a binary search to speed it up from n to n log n, or from n to log n. And I feel like that would be, a good way of saying that you understand sort of what the potential faster way to do it is, but you kind of can't implement it off the top of your head. I'm not sure, Max, you might have to help me with that one from a kind of an interviewer perspective. If it's the leftmost bound, as you can see on 14, 15, there are only 2 conditions. Yeah, because you never want to go to the right, because you never want to go higher. Yeah, this makes sense. Left equals mid plus 1. Stupid C++ lower upper bound function. I've never worked with C++, but I assume it's something to do with it being inclusive or exclusive to numbers. I love the fact that there's just a constant in JS for infinity. Because, yeah, I mean, yours is n log n, mine, I think worst case is just n squared. Because, I mean, the worst case, we could have all zeros and then just a 1 down here, and that's what we would return. Let's go ahead and go back to 1. Let's go to solutions. It's a 0 upvotes, I think he said. There it is. Naive solutions to recursively or iteratively replace n until it's below 10, yeah. Intuition is to see that each iteration of n remains a space distance from being divisible by 9. Which is the 10. Okay. We can see 2, 3, 1, which is 6 from 2 to 5. We check if n is divisible by 9. If so, we return 0. Okay. Otherwise, we return the distance from being divisible by 9. This is such a clever way to do it, because let's say we have 10, the distance would be 1, because, yeah. And, for example, we have something like 1, 2, 3, right? 123 mod 9. Didn't follow the optimal solution, fine. Mind re-going through it or not? Oh yeah, it's a mind bender in itself. So I want to try. So let's try something like 17 here, right? 9, 18. So this would be. Oh goodness, what is the mod of? Let me pull up my programming calculator. Where's program? It's interesting because Windows has like a built-in programmer calculator. I'm not sure when you would ever 17 mod 9 is 8. But I think that'd be cool. Yeah, no, this kind of makes sense the more you think about it. Okay, let's go ahead and try and understand this one. Let me pull up their solution. Copy it out to put it into like the bigger window so I can type there as well. Crap, what did I copy? Just copy everything. Alright, let's do that. Paste it in. That is not what I wanted. Okay. Submissions accepted. Gotta make sure we actually copy the right thing here. Thing is, I don't know if this is actually the like quote-unquote optimal solution, because Max did mention that it might be possible to do it in O of 1 space, though I don't know time complexity-wise if that would be better or worse. Okay. Cool. So, let's see what we were doing here. So, what they're doing is keeping track. We're pretty much going to be doing a O of tree depth space. Yeah. We're going to be doing a in order and reverse in order traversal. That's why we have a LNR stack and an RNL stack, which stands for left node right and right node left. So we have a right node left stack and a left node right stack. What we do, from my understanding, right, push all left and push all right, what these methods do is go as far to the left as they can and as far to the right as they can from the given node to add all of those to the stack. So calling push all left, for example, here would push the 1 onto it, and then calling push all right here, I think would push 5 and 1. So this is going to push all connected left nodes in a line, and then push all connected right nodes. And then what we want to do is we take the root and we want to push all the ones that it's connected to. Because I think from my understanding, right, the reason this works is because going all the way right will give you this last node, and then this one will be, yep, left node. And then pretty much just repeat these steps until it's empty. So yeah, we're gonna pop off from these stacks. For example, popping off this one will give us the 1 on the left. Popping off this will give us the 1 on the right. This never triggers. And then L and R node, we push all the left nodes. There's nothing to push. There's nothing to push on the right. So we continue. We pop off. The next one here would be, I think, 5. Next one we pop here would be 5. And then the next one here we pop would be 5 as well. And yeah. And then at that point, there's only one element left in the stack, which would be a 9. And that's it. Very clever. Definitely something that's kind of beyond me when it comes to these trees. I'd say trees are a fairly strong data structure for me. However, this is like next level trees. I hope I never have to do this in an interview again. But yeah, overall pretty solid, pretty solid. This was a very interesting room. This question I definitely could be optimized with a binary search, but you know, implementing a binary search in a stressful interview setting is kind of scary if you're not super confident with it. All right, I think that's going to be it for me today. Good set of questions. I hope to be back tomorrow. Honestly, somewhere within this hour. It just depends on when I get kind of everything set up. I mean, you're chilling, Max. I mean, granted, how does it feel? I'm not sure if you've ever re-interviewed after like getting a position, but I imagine it's not fun when you've been kind of in the industry. You know, let's say you've gone from like an L1 engineer to like an L3. And you're like, okay, cool, I want to hop companies. And then you have to go and relearn all the leak code questions, relearn the patterns, so you can actually pass the technical interviews. It seems like it's just not a fun thing to do. And it makes switching jobs, it's like the one thing about switching jobs, at least in this market, that seems like a downside. Yeah, thanks, Ditching. It was a pretty fun one. The fact that there's just a one-liner to do this is kind of still very shocking to me. All right. The fact that I went into like hot potato routing for like networking switches is solution is to never stop leak coding. Yeah, I wish that the streak would work based off of just general problem solved, not new problem solved. Because I mean, I understand you can keep solving the same easy one, but you're not cheating anybody besides yourself. So, because I mean, I've been solving problems for yeah, I've been solving problems pretty consistently, and I mean, I don't really care about the streak as much, but you know, it still would have been nice to see on the progress chart here, because it shows them all as empty, but that's just because I haven't solved any new ones. Yeah, haven't re-interviewed. It's something I'm not particularly looking forward to when I'm graduating in a few weeks here, so I'm not particularly looking forward to in a couple of years when I need to re-interview for another position. Yeah, one leak code a day keeps pulling away. Yeah, I'm just gonna keep solving is palindrome over and over. Should help. But yeah, it's definitely, man, the amount of badges. 85 of these things. Is Apex the, yeah, 9 problems in a day. This is when I kind of had nothing better to do. Alright, yeah, that's gonna be it for me today. Thank you everyone for watching. Hope to be back tomorrow about the same time, solving more problems, learning more interesting techniques like this freaking in order, reverse in order traversal for solving an is palindromic tree. Thank you everyone, and take care.